Looks very good, and you can go.
Okay, thank you, Chairperson. Hello, I'm Atsuyoshi Saimen from Mitsubishi Heavy Industries. Today, I'd like to talk about hybrid system falsification for multiple constraint parameter synthesis, gas turbine case study. This work is a collaborative research with National Institute of Informatics, Japan. First of all, let me show the summary. The purpose of this research is a quality assurance of industrial gas turbine, one of Mitsubishi's products. As engineer's task, they design time series fuel supply in multiple constraints at odds. The problem is that this task is laborious because of manual parameter tuning in trial and error manner. So in order to automate this task, we applied parameter synthesis by hybrid system falsification. In this slide, we faced two challenges. Today, we show how we resolved. And the point is that our case study is a new type of application of falsification in industry domain. Now we go to the introduction. Here is the outline of my presentation. Firstly, I introduce a gas turbine and load rejection. And this figure shows an overview of a gas turbine, the core component of power plants. And gas turbine takes air, and the compressor makes this air high pressured and feed it to the combustor. The combustor sprays fuel, then ignition occurs. High temperature flow enters a turbine, and the turbine transforms this thermal energy to rotation energy, which drives electric power generator. For industrial gas turbine, safety, efficiency, and high availability are essentially required for stable service. To meet with these requirements, there is a safety function called load rejection. When the load rejection is needed, the operator cuts away power generator immediately from power supply network. Then the fuel is automatically controlled to decrease the rotation speed and at the same time to keep flame for quick restart. Here, there is a trade-off. If fuel decreases too quickly, the issue called flame loss occurs. Once this issue occurs, much fuel, time, and efforts are needed to restart. In opposite, if fuel decreases too slow, the rotor excessively speeds up and causes equipment damage. So in order to prevent these issues, fuel control after load rejection should be carefully designed. In next section, I explain our parameter synthesis approach and the challenges. At first, let me show the comparison between previous approach and ours. In previous approach, parameters for fuel control are manually tuned by human expertise. They carry out simulation and observe performance, try other set of parameters in trial and error manner. So it takes 7 person days. So we try to develop the method to tune parameters automatically by hybrid system falsification, which takes 3 hours for iteration. Here, let me introduce the hybrid system falsification. Hybrid system falsification is a logic-powered search-based testing for the quality assurance on cyber-physical systems. Its goal is to find an input U, which output MU violates the given logical specification phi. The specification is described with signal temporal logic. In this example, specification is that speed is always below 100 during time 0 to 30. Next, we introduce optimization-based falsification. In optimization-based falsification, the robustness is introduced. Robustness is a quantitative satisfaction or violation of output MU against specification phi. Using robustness as objective function, hill climbing style optimization algorithms such as simulated annealing can be used to iteratively search its input whose robustness is negative. The negative robustness implies that input violates the specification. Now we turn to the parameter synthesis. Our problem is automated parameter tuning. It can be thought as parameter synthesis. Parameter synthesis is a problem to find a parameter V such that output MV satisfies the specification phi. The difference from falsification is just violates and satisfy. So parameter synthesis can also be solved in optimization manner. It means that parameter synthesis can be solved by falsification solvers. From here, we go on to our specific problem. The gas turbine model for load rejection has 30 parameters that are static variables and 4 time series output. The requirements consist of 2 mandatory and 3 desirable ones. Most of them are related to unsafe region represented by a red area. Output image which satisfies the requirements is represented by green line, and gray line represents violating one. The requirements written by natural language is translated to STL formula. Then a specification is defined as conjunctive one. Recalling our problem is parameter synthesis. We try to find a parameter which satisfies this specification. So falsification 2, we give specification not phi because falsifying not phi is equivalent to satisfying phi. Now we have a gas turbine model and its logical specification. We applied falsification 2 for our problem, but we faced 2 challenges. First one is conjunctive synthesis. Our parameter synthesis problem have many requirements, so its specification conjunctive at odds. This type of synthesis cannot be solved straightly due to the difficulty called scale problem. For this challenge, we reduced the synthesis problem to multiple constraint optimization and applied multiple constraint ranking, MCR. The second one is that some requirements are given in geometric conditions. For example, output H1 and H2 should not reach region 1 and region 2. Here, we want to reflect 2 types of violation, spatial and temporal, to robustness. To do this, we extended signal temporal logic, introducing the new modal operator area modality. In next section, we'll explain the countermeasures more detail. For first challenge, conjunctive synthesis, let me explain scale problem. Optimization-based conjunctive synthesis problem is described like this. In usual semantics of robustness, semantics of conjunctive requirement they are defined as the supremum of the robustness of each conjunct. Example output is shown at middle. And in the left case, both 2 requirements are violated. And in the right case, the requirement not phi 2 mandatory is satisfied. However, the robust semantics indicates they have same robustness. It means that contribution of small-scale conjunct is masked. In this situation, the hill climbing algorithm deems them flat, and optimization-based search is impeded. Such a problem is called scale problem. To escape from this, we reduce the conjunctive synthesis to multiple constraint optimization. One conjunct is selected as the optimization target, and robustness of other conjunct is separated as constraint function. There is another problem. In each conjunct, the scale of variance are different, and that makes hill climbing optimization ineffective. So we applied multiple constraint ranking, MCR. MCR is an algorithm for constraint optimization, which is applied with evolutionary computing, such as particle swarm optimization. The main idea is that it evaluates individual not by combined values, but by ranking in individuals. By applying MCR, constraint optimization can be scale invariant. For second challenge, requirements in geometric condition, we wanted to measure the degree of violation in both spatial and temporal terms. In usual signal temporal logic and its robust semantics, the degree of violation is measured spatial. Here, we introduced the area modality. The main idea is to measure the degree of violation by area. The robustness of area is defined by integration of spatial robustness over time. In this way, we capture both spatial and temporal robustness. Now we turn to our problem. By applying area modality, we refined our desirable requirements. And now we show the result of parameter synthesis. Let me recall our problem. Our problem is a parameter synthesis under two mandatory requirements and three desirable ones, and they are at odds. In this section, we report the result comparing two baseline approaches. First baseline is manual. It represents manual synthesis by domain experts. Machine support is limited to simulation. Observing performance and adapting parameters were done manually with experts' domain knowledge. As we show the simulation result in next page, the quality of this approach is acceptable, but takes much longer time, 7 person days. Next baseline is breach. In this approach, we used breach, a well-known material-based falsification solver. We gave breach the conjunctive specification. As a result, breach couldn't satisfy a mandatory requirement after 3 hours iteration. So it didn't meet practical demand. MCR plus area is our approach. In this approach, we implemented MCR plus area modality on top of breach. And we reduced the conjunctive synthesis to multiple constraint optimization. And compared to baselines, our approach was better on quality and cost. In next page, let's see the simulation result performed at each synthesized parameter. And these figures show the simulation result carried out with synthesized parameter. There are 2 notable points. The first one is that MCR plus area satisfies most requirements, including 2 mandatory and 3 and 2 desirable. Only desirable 3 requirement is violated. we think that scale-free optimization by MCR contributed to find a parameter which satisfies these requirements effectively. The other one is that MCR plus area violates desirable 3 slightly, but very short time. We think that the robustness of area modality contributed to shorten the temporal violation. Lastly, let me conclude this work and mention future work. In conclusion, for parameter synthesis problem of industrial gas turbine, our approach MCR plus area successfully synthesized the parameters. Quality and cost were better than others. For future work, we will try to integrate the logic-based automated tools in industry practice. And also, we want to try to establish the collaborative design process with domain experts and automated tools. And that's all of my presentation. Thank you very much for your kind attention.
Thank you. Are there any questions? Please either post them in the chat or raise hand and let me know, or just even speak up. I can start with 1 or 2 questions. So regarding the conjunctions issue, you said that in the end you rank individuals, and this part was not completely clear to me. Can you explain? So this was the last aspect before you got to the modality.
Sorry, let me confirm your question.
So in the discussion of the multiple constraint issue, you finally said that to avoid the scaling issue, you rank individuals. Can you explain this point? Maybe if you go on slides, you should go a bit further, I think.
Okay. Specification like conjunctive falsification solver usually a falsification solver cannot falsify the straightly. So we changed the translated the problem to multiple constraint optimization, and MCR is the one of kind of algorithm to solve constraint optimization effectively. So this algorithm uses evolutionary computing.
Yes, that's the slide I wanted to ask about. Exactly. Yes, thank you. Now, what happens here?
Okay, this is sorry. This is Ichiro Hasuo speaking as a call. Can I answer your question, Tarmo?
You may.
Yeah.
Yes.
Okay. Thanks.
I'm a bit confused about exactly this slide. Yes.
Yeah. So the like we are doing evolutionary computation, right? So we have a population of individuals, and we have to choose the fittest, and then remove all the others. And then usually, I mean, the problem is the definition of fitness here, right?
Exactly.
Yeah. And then usually if you see, but then there are multiple constraints, therefore multiple fitness functions. So the question is how to superpose these different fitness functions, right?
Yes.
And then usually we would take the minimum, numerical minimum, which is a bit strange because these different fitness functions, they might have different scales. That's why we take the ranking. So like as it is shown on the bottom of this slide. Yeah, like there's a table right on the bottom of the slide.
Oh, so you take the ranks according to the different conjunct.
Exactly.
Based
So
on this, you calculate. Yeah. Now I see. This is the lower part of the slide. Yeah. Not the absolute values in terms of these whatever.
Indeed.
Robustness indicators, but just the place in the ranking for every conjunct separately. That explains everything. Thank you. Let me see if there are other questions. There don't seem to be at the moment. I have one more, which I can quickly ask.
Perhaps Andre is raising his hand.
Oh,
that's right. I'm sorry.
Yes,
maybe
please.
my hand raising isn't working. A very nice talk. I have a question about the validation at the end of the day. And it was on slide 20, where you showed the individual qualities of the three designs and so on. But what I didn't quite understand is, how did you establish the quality and the violation of the individual designs? Was this by simulation or was it by some other means? In other words, how exhaustive do you know something about the quality of the three designs at the end of the day?
If I may answer, can I answer, Atsuyoshi?
Yes, please.
Okay, yeah, thanks. So it's by simulation, and note that the system is okay. So the system is, I think the system was okay. So the system was, I think, modeled in Modelica, but it's a deterministic system. So once we fix the parameter values, then its behavior is deterministic. So yeah, so under this deterministic setting, we run simulation, numeric simulation.
All right. So the only thing that could have tampered with it is sort of a discretization issues in the Modelica simulator, but it is a deterministic system, so that's why sort of you have a good handle on it in reactors. Thank you.
Indeed. Thanks.
Thanks.